Now this is a problem from the lecture notes, and some of you ask a lot about this question. So we are going to use this following fact that we have proven in the previous videos. So if we have two sequence of functions, f of n and g of n, and they both uniformly converge to some functions f and g, if they both bounded, the uniform limits are bounded, then we can multiply them, and the result is the multiplication of the uniform limits. So I'm just gonna use to eliminate this 3, right? Because if I can prove without 3, just ln this thing is uniformly convergent on this interval, then the power 3 is also uniformly convergent by using this fact. So let me prove this claim. Why I am aiming to prove uniform convergency? Because if I can prove this sequence of functions are uniformly convergent on this interval, then I can interchange with limit, so I can easily calculate this integral, because in this case it is very hard to calculate. So claim ln 1 plus 2 and x squared over square is uniformly convergent on E2e to ln 2. Why ln 2? Because it is my pointwise limit. So let me start. So fix some x in this interval e and 2e, and then start to calculate this limit, and goes to infinity. By the way, look at these values inside of this interval. There's no such pathology to make this 0, 1, blah blah or singular. So I can just consider this x as a fixed value, fix some constant value inside, so I can just focus on this n. Now ln 1 plus 2nx squared over 2 plus nx squared. Since ln is continuous, you know that I can interchange with limit and ln, because that's how continuous functions are working. So when n is going to infinity, just consider n is the variable, not x. X is just a fixed constant for the time being. So since we have the same power of n, you know how to calculate the inside of the limit of inside, the coefficients, right? 2x squared over x squared. So you get 2. So this pointwise limit would be ln 2. Okay, nice. Okay, so as I repeat myself, if x was allowed to be 0, if you put 0, 0, they will eliminate. You will have ln 1 over 2, but there is no such case because x cannot be 0, because we are in this interval. So now we have some pointwise limits. I'm gonna prove that this is indeed a uniform limit. Now another claim. No, it is the same claim. I thought that it was just pointwise. Okay, it is uniform. So let me prove. How can I prove? Yeah, just write the definition of supremum. Supremum fnx, but in our case fn is just ln without 3. So without writing generality, let me just write everything explicitly. ln 1 plus 2nx squared over 2 plus nx squared minus ln 2. It was my pointwise limit. So I'm claiming this supremum would be 0 when x inside E to E. Okay. So before calculating the supremum, let me just analyze the inside. You remember the rules of ln. When you have some subtraction, this 2 would become the division inside. So this is just sup ln 1 plus 2nx square or 2nx square. And I have x in E to A. Close. Okay. Now let us analyze this ln. Okay. ln 2n square. Let me put plus 3 minus 3 divided by the same thing, right? So I will get 1 minus 3 over 4 plus 2 and x square. Okay. Now, but we have some prior information from the calculus courses. For example, recall if x is bigger than 0 but small, okay, let me then put 1, then ln 1 minus x is less than minus x, and it is bigger than minus x square over 2. Okay, in our case, then this thing, this ln, let me do it like this, minus 3 over 4 plus 2nx square minus 1 over 2 square is less than ln 1 minus 3 over 4 plus 2nx square is less than minus 3 over 4 plus 2nx square. Now I'm gonna use this inequality, okay, I'm gonna use this inequality to calculate this supremum. Okay, as you can see, each side of this inequality is gonna approach to 0, right? Because we fix some x inside of this interval, whatever it is, we don't care. In this case, that's why we don't care. So if you take the limit as n goes to infinity, this gonna be 0, this gonna be 0, this gonna be 0, so middleman is gonna be 0. So the supremum is gonna be 0, okay? Because when you take the absolute value, okay, let me explain fully. Because then ln inside of the absolute value 1 plus 2nx square over 4 plus 2nx square is gonna be less than absolutely şunu kapattım. Okay, minus 3 over 4 plus 2nx square minus 1 over 2 3 over 4 plus 2nx square. As you can see, this gonna approach 0. As n goes to infinity. So by squeeze theorem, right, this gonna be also 0. So we have shown that, right, this, ne yapıyorum ben ya? This supremum in terms of n, okay, this is a sequence of n, right? When you calculate the supremum, it is it is dependent on the index n. So when you take the limit in terms of n, I mean the supremum is gonna approach 0 as we have calculated below. So it is equivalent to saying that this is indeed a uniform. This limit is indeed uniformly approaches to ln2. So I'm gonna use this recall 3 times or 2 times, such that I will find that this ln3 is also approaching to ln cube 2, right? So we have found that. Let me just finish the question. So this ln, what was the function? Let me just see. Ln cube 1 plus 2nx square over 2 plus nx square is uniformly on e2 ln cube 2, or if you confuse yourself, ln 2's cube. Since it is uniform and everything is continuous, of course this is a constant thing, so it is also continuous, so it remain integrable. So when we apply to the question, we will have limit, so n goes to infinity ln cube, whoops, there should be some integral sign, sorry, ln cube 1 plus 2nx square over 2 plus nx square dx is, since it is uniform convergence, is equal to integral e to 2e ln cube 2 dx. But it is very easy to calculate because this is just a constant number. So this is multiplied by the length of this interval or the measure. So it is e times ln cube 2 as a result. So that this uniform convergence is that strong, okay? Now let us understand this question. We have a convergence sequence of real numbers. So these are not functions, they are just numbers. The good old real numbers, sequence of real numbers. So we have extra sequence of functions such that they satisfy this inequality, okay? So we have supremum and these are less than this thing, okay? So it's like a Kaczor criterion, but a bit stronger than it, okay? Actually equivalent, because in real numbers every convergence sequence is Cauchy and vice versa. Every Cauchy sequence also convergent. So since it is convergence sequence, so it is a relation for Cauchy sequence. It means that it will be convergence and less than some epsilon for any given epsilon. So it will force that this supremum also will be as small as we want, so that it will prove our Cauchy criterion. Okay, let me prove first, or state first. Pointwise limits fn's are converging to, say, some f. Function f. Now for any x, okay, for any x in this set A, we have fn x minus fm x is less than supremum fn x fm x in A obviously, right? Because it is an upper bound. And this is less than am. Satisfying nm. So I'm looking for there's some condition or not. No, I think for every nm it is correct. Interesting. Okay, it's stronger than what I expected. Anyway, so since for any x this is satisfied, you can fix some x so that this will be less than this, and by the Cauchy criterion in the real numbers, this will be less than any epsilon given. So it will prove my pointwise convergence, okay? So at each x, it approaches to some real numbers. So if you sum them up, I mean, if you collect them up and create a new function which is called x, f of x, then it is your pointwise limit. Okay, this is finished. You can prove it. It's not our main job to prove it is pointwise or not. Obviously pointwise. Now I'm aiming to show this f of x, which is collected by this point by point, is my uniform convergence function. Okay, so I mean that fn's are uniformly converging to f. So let me prove. First claim fn are uniformly approaching on A to F. Proof. Given any epsilon bigger than 0. Okay, so I want to find some n0. There is n0 in natural number. I'm gonna determine this n0. I mean it is already determined because of the convergence of the sequence an. Okay, as n0 such that if n is bigger than or equal to, okay, mn, I mean m and n are bigger than n0, then f of n x minus f of mx is less than an minus am, and this is less than epsilon. Okay, now I'm gonna take the limits of the both cases. Okay, I'm gonna take the limits here and here at the same time, so, or just left hand side, because this epsilon is constant, right? It is fixed at the beginning, so it is a fixed value. Since if you are taking the limits and every sequence or every sequence is less than some number, limit also less than this fixed number. So I'm gonna just take the limits m approaches to infinity of f of n x minus f of m. By the way, let me also add, this is happening for any x. Okay, this is also be seen here. Okay, here f of m, but this is equal to, since absolute value is continuous, f of n x minus limit m goes to infinity f of x. But this is by definition the pointwise limit of fn's, which we have proven to be fx. And this is less than epsilon. So at the end we have found that f of n x, by the way, for any x in A, f of n x minus f of x is less than epsilon, and we have just proven original, the first definition of the uniform convergence. Okay, finished. Now let's look at this question. Show that the limit function of uniformly convergent sequence of bounded function is bounded. I mean, I have sequence of functions, okay, fn's. Each of them is bounded for all n. And assume that they are uniformly approaching on A to some function, uniformly converging to some function. Then it says that f is also bounded. It's like in the continuous case, if each fn is continuous, then if it also has a uniform convergence limit function, this also continues. The similar idea, but it is very easy in this case. So since fn's are approaching to or uniformly converging to f on A, for epsilon equals to 1, since it is uniform, I can choose whatever I like. There is n0 in natural number such that if n bigger than n0, f of okay, sure, let me put f of x, which is f of x minus f of nx plus f of okay, n0, let me say n0 x. I can rewrite this, or not rewrite. I can use the triangular inequality such that this f of x plus, not minus, f of n0 x plus f n0 x. Okay, so I know that this is bounded by assumption, and this is less than epsilon, which is 1. So this whole is less than 1 plus whatever the bound for this n0 is, let me call m0. So the original function is less than this, but since I am applying the definition of uniform convergence, this thing happening for every x. So this is true, holds, let me change the color, holds for all x in A. It means that our function f of x, the limit function f of x, is less than some constant, some fixed constant for any x in the domain or A. Okay, so this I part is finished. For the I part, double I part, the answer is negative, I guess, because consider the following. So this example is classical, but a bit weird at the first sight. So consider fn's which are defined on this interval 0 infinity, two real numbers, such that f of nx is minimum of x and n. Okay, as you can see, for each n fnx is bounded by n, bounded for all x. For example, I mean that fix an n natural number, this fnx is minimum of x n or n. Okay, and this is by definition less than n, and this is happening for every x in this interval. Okay, so this is true. So I've shown that these fn's are bounded. So let us calculate the pointwise limit. Fix x in 0 infinity. Calculate the limits n goes to infinity f of n x. Limit n goes to infinity min x n. So since x is fixed, after some point n is exceeding x, right? By Archimedean principle. So since n will be bigger than x, the minimum of thing would be x. So this pointwise limit will be x. Okay, so since it is true for every fixed x, so I can conclude that fn's are pointwisely converging to x. But as you can see, this x is not bounded. Not bounded. So counterexample, or yeah, it does not hold for the pointwise convergence here.